Hello everyone, welcome to this sixth lecture on radiative heat exchange. For this lecture we will discuss how we treat radiation between multiple surfaces, and we will do a special case of the multiple surfaces where one of the surfaces is adiabatic. We'll first do that for black bodies, and then we will see what kind of special considerations we have to do for gray bodies. Finally, we will have a brief discussion on so-called effective view factors, which lumps together the view factors for multiple surfaces when calculating the net heat exchange, which is typically what you are interested in. Sources for today are chapters 3.13 and 3.14 in the compendium. So let's jump right into it. So last time we introduced the concept of surfaces acting as either sinks or sources or adiabats, depending upon the relation between the radiosity and the received radiation. In this lecture, we will see how these surfaces interact. So a practical example we've shown in the figure here is to calculate the radiative heat loss from an open crucible that has some refractory walls with area AR. So these are these orange walls that we have here. So these are adiabatic. The crucible contains a hot metal pad which acts as a source, and this hot metal pad has then an area A1 and a temperature T1. The radiation will leave the system through a surface A2. Sorry. And this surface A2 doesn't necessarily have to be a physical surface. It can be the open area of the top of the crucible. So the first place we will start is to assume that the surfaces A1 and A2 are black. So we will introduce a few simplifying assumptions. First one is that we only have three surfaces. Surfaces are AR, which is refractory, which is adiabatic, A1, the hot surface, A2, the cold surface. And all of these surfaces only see each other. We are considering steady state conditions, and that means that the surfaces are isothermal, constant temperature. That, of course, simplifies things because we will then just have TR, T1, and T2 as constant temperatures. Then we require that the surfaces are diffuse and that they follow Lambert's law, allowing us to utilize the view factor concept for our calculations. And then the fourth assumption for this part of the lecture is that A1 and A2 are black. And in half an hour or so, we will see how this plays out in the case where A1 and A2 are gray. Sorry. Since the adiabatic surface can be considered as black, we can calculate the heat flow between the source and the refractory, or the adiabatic surface, in the following way. So Q1R, so that's the heat flow rate from surface number 1, that's the hot surface, to the refractory. That is equal to A1, let's use a red one, A1 times F1R times EB1, which ultimately depends upon the temperature of that surface. Correspondingly, we can calculate R1, which is the amount of, which is the net heat transfer returning to the hot surface from the refractory. That one will be AR FR1 times EBR. Okay, so there is a mutual exchange of heat between these two surfaces. So the next step is that we utilize the reciprocal relation that we introduced in the last lecture, stating that AI Fij equals AJ Fji. That allows us to write A1 F1R, we had here, as AR FR1 that we had here. That results in a net heat flux, Q1R, which of course is then Q1R minus QR1. That's the difference in heat flux. So net heat flux, and then we can put the areas and U factors on the outside, and we then get a quite simple relation for the net heat flux from surface number 1 to the refractory. We have a common area and refractory or view factor coming from the reciprocal relation, and we here have the difference in emitted blackbody radiative flux. So that's from surface 1 to the adiabat. Correspondingly, we can calculate the net heat exchange between the refractory and the sink. That would be QR2. Again, we utilize the reciprocal relation to write this term as the same for both. And we have then the difference in EBR and EB2. So, typically, we will know the value of EB1. It's essentially the temperature of the hot metal pad. And we will typically also know EB2 because that depends upon T2, which essentially is the temperature of the environment. Of course, the question is then, what is EBR? Excuse me. So EBR depends upon the temperature of the refractory. So how would we calculate that? Well, R, the surface R, is adiabatic. So that means that the net heat flow for this refractory must be 0. So 0 equals Q1R minus QR2. That means that these two net heat fluxes, the one coming from the metal pad going to the refractory, it has to exactly balance the one going from the refractory to the environment. If not, heat will accumulate. So this allows us to write the following expression. Just by substituting for Q1R and for QR2, as we have just calculated. This gives you a single expression for EBR, and EBR is essentially given by the temperature of that surface. So it depends upon the view factors and the temperatures of the surfaces from which it is receiving radiation and to which it is emitting radiation, that is the exit of the crucible. So, as I stated here in words, just like I just said, the equilibrium temperature of the refractory, TR, is determined by the values of T1 and T2, as well as the geometry of the system, for example, expressed by means of view factors. Now, the heat transfer rates that we have calculated are between two surfaces. The net heat flow in a total sense will have to be expressed by means of all surfaces involved. So the net heat flux for surface number 1, so that is what is leaving surface number 1, has two contributions. It has one contribution, which is a direct transfer from surface number 1 to surface number 2, and it has a sort of an indirect contribution, which is to the refractory, Q1R. Now, since R is adiabatic, the net heat transfer rate for surface 1 must exactly balance the negative of the heat transfer rate for surface 2. If not, energy would not be conserved. So, we can, for a black body, calculate this Q12. And we have already calculated Q1R. Then, in the extension to this one, we have just used the reciprocal relation in order to rewrite this particular term. We will reuse this equation later, so we call it double star. Going back to equation star, which was this one, relating Q1R to QR2. Rewritten here. We see that we can find here an expression for EB1 minus EBR here. Of course, you have to play a bit around because you have an EBR there as well. So show this for yourself. But this is the expression that you get. And what we now want to do is to introduce this particular term here in double star. And the reason for that is that that will give us an expression which is not dependent upon EBR, that is the unknown temperature of the refractory. So as I said, we introduce our result from equation star into double star to find the net heat transfer rate from surface number 1. The first term here is just the green one, Q12, we have here. Then we had AR FR1 multiplied with EB1 minus EBR, which we have found an expression for here. Right? So we substitute and we get the following expression. Oops. This is the same. This is the same. And here now we have what we got from equation star. As I said, this is no longer a function of EBR. It only contains EB1 and EB2, EB1, EB2, which depend upon the known temperatures, which greatly simplifies the calculation of the net heat transfer rate, which ultimately is what we are interested in. So, using some simple manipulations of the expressions, we arrive here, where we have taken out the common factor EB1 minus EB2. And of course, in this expression, we see that we have a AR FR1 and AR FR2, and these we are free to interchange or interexchange with whatever terms that we have available due to the reciprocal relation. So we will also look at this from a electrical analogy corresponding to Ohm's law. So we write this term as an electrical resistance. So introduce resistance as 1 over R net, because it's referring to a net heat transfer rate. It equals to A1 times F12 plus 1 over 1 over AR FR1 plus 1 over AR FR2. And we call each of these for RR1 and RR2, where the subscript R is due to these surfaces being refractories. So that gives us a simple relation for the net heat transfer rate. It equals to the difference in emitted blackbody flux divided by the net resistance. And again, this is analogous to Ohm's law, where we say that the difference in voltage equals to the current times the electrical resistance. Instead here we don't have a current, we have a heat flow rate, and instead of voltage we have a difference in radiative flux. So some evident observations. Of course, if the adiabatic surface cannot be seen from both A1 and A2, then F1R will then be equal to F2R, will be equal to 0. And in that case, the net heat transfer rate will essentially be A1 F12 times EB1 minus EB2, which is the same as Q12. That means if the adiabatic surface is not visible, it does not intercept any radiation, and the system will then behave as though that surface wasn't there. Obvious, hopefully. Let us now move on to an extension of this where we consider gray surfaces. So A1 and A2 will be gray. And the reason for that is that real surfaces are more often gray than black. And consequently, we will have to replace the black surface emissive power, EBI, with the radiosity, which then contains a fraction of the emissive power depending upon the emissivity of the surface, but it also contains a fraction of the incoming radiation based on the reflectivity of the surface in question. In the last lecture, we demonstrated that the net heat flow rate from a surface can be written as the emissive power minus the radiosity divided by the reflectivity divided by the surface area divided by the emissivity, or multiplied with emissivity. And we wrote this term as Ri, which is the so-called surface resistance. So go back to the previous lecture if you missed that important point. It's right after we have reintroduced the same figure as we introduced in the first lecture. So for our system, we have three surfaces. We note that we can express Q1 net, which is then the net heat transfer from surface number 1, as EB1, which is the black body emitted emissive power, minus J1, which is the radiosity, and then we will divide it by R1. That's the net heat transfer rate. Correspondingly, for surface number 2, we would have EB2 minus J2 divided by R2. Now, since the third surface is adiabatic, whatever heat is coming out of surface number 1, which is the hot one, has to be balanced by a negative heat transfer rate at surface number 2. So that means that Q1 net can also be expressed as J2 minus EB2 divided by R2, which is the negative of this expression. And of course, what is important to note here is that J1 and J2 are unknown. That is because they are not only dependent upon the temperatures, but also upon the reflectivity, thereby giving a portion of reflected radiation coming from the surrounding surfaces. So these are still unknown functions. If we now look at the final result that we derived for a black surface, we found that the net heat transfer rate could also be expressed as EB1 minus EB2 divided by the net resistance. So inspired by this, we replace the emissive power by the radiosity for a gray surface. So Q1 net is now equal to the difference in J1 and J2 divided by a R net for our gray surface. So we now have three equations. All of them are related to Q1 net. They have three different resistances. They have the unknown radiosities, but they also have the known blackbody emissive powers. What is interesting to note is that if you sum all of these, the radiosities will cancel, and you get the following expression. Q1 net multiplied with a sum of resistances, R1 plus R2 plus this R net, equals to the difference in the blackbody emissive power. Or if you want, you can of course solve this explicitly for the net heat transfer rate. Again, we have this difference in emissive black power divided by the resistances. R1 we have already defined, R2 we have already defined as well. They are equal to rho 1 divided by A1 epsilon 1 and rho 2 divided by A2 epsilon 2. This should be 2, not 1, sorry. 2. So, evidently, the total resistance, so the total resistance for a system with gray surfaces is R1 plus R net plus R2. And the contributions R1 and R2 account for the non-ideality or the grayness of surface 1 and 2. Why? Well, they depend upon the reflectivity, which is not equal to 0 for gray surfaces. R net applies to the geometry of a equivalent black surface. So that's a geometrical effect. The resistance becomes higher due to the grayness of the surfaces, and that ends up in a smaller heat flux. Than if you had black surfaces, because our total gray is greater than R net. And that coincides with what we found in our discussion on radiation shields a few weeks back. Now we'll have a slightly different discussion relating to effective view factors. And this is a concept which you would encounter quite frequently in the literature when you are looking at a three-surface problem. So if we assume, again, black surfaces, so the emitting and the receiving surface are black, so A1 and A2. We have a Q1 net equal to the difference in the emitted power divided by this R net, which is a geometrical factor, defined as here. 1 over R net equals A1 F12 plus 1 over these specific resistances. In such a case, so for a black surface, we define that the net heat transfer rate Q1 net equals to A1 times this F12 with a overbar multiplied with the difference in emissive power. This is to have it analogously to our previous definitions of the view factor. In this case, the product between the area A1 and this view factor is then equivalent to 1 over the net resistance, and that we have introduced already. This F12 with a bar overhand is called the effective view factor. So we lump the effect of radiation going to and from the refractories or the adiabatic surface into one complete factor that we have here. That's the effective view factor. If the surfaces are gray, then we need to include the corresponding surface resistances. It's just shown. We have a R1, which is due to the non-ideality of the first surface, and we have a R2, which is due to the non-ideality of the second surface. We have to consider these in addition to the net resistance, which is purely geometrical. In that case, the total resistance of the gray surface equals simply to the sum of all of these contributions. And in that case, we write as before that the net heat exchange equals to the area of the hot surface multiplied with this F12, and now we use a tilde above the F, and the definition is simply that 1 over A1 multiplied with F tilde 12 equals to the total resistance we have here. And what is then interesting to note also is that, of course, the net resistance depends upon the effective view factor for a black body. So if you see this one, this is a lumped parameter for gray bodies. And if you see this one, this is for black bodies. And of course, as always, people tend to forget what notation means when you read things in books, so make sure that you are using the correct effective view factor. If not, you will get some nasty surprises. Finally, I would just like to comment on what you will do if you have 3 arbitrary surfaces. So you don't necessarily have an adiabatic surface present. In that case, you will have to introduce a quite decent amount of linear algebra, because there are 6 heat flows that have to be considered. You'll have 1, 2, 1, 3, 2, 1, 2, 3, and 3, 1, and 3, 2, with all of the corresponding resistances. So needless to say, this will result in a set of linear equations. So you'll have some matrices that you will have to invert, etc. It's not very convenient to present in this format, so I suggest that you look to chapter 315 in the compendium, and then you can read this on your own if you at some point in your life need to realize these kind of calculations. That's it for today. Thank you for listening, and hope you're well.